This is a transformer, the architecture inside every large language model. Text goes in at one end and a prediction comes out the other. Let's build it one piece at a time. It starts with your text. We split it into tokens, common chunks of characters, not quite words. Each token becomes an ID, a row number into a giant lookup table. That row is the token's embedding, a long list of numbers, say 768 of them. Its starting meaning. But attention alone treats every position the same. So we add a positional encoding, a second vector that stamps each token with where it sits in the sequence. Add the two together, and every token is now a single vector, carrying both its meaning and its place. That is what we feed into the stack. Inside each block, the first step is self-attention. Every token looks at the others and decides which ones matter. To do that, each token is projected into three vectors: a query, a key, and a value. The query is what this token is looking for. Each key is what a token offers. We take the query and dot it with every key. A larger dot product means a stronger match. We scale the scores to keep them stable. And in a language model, we mask the future, so a token can only attend to the words before it. Softmax then turns those scores into weights that add up to 1. Finally, we add up every token's value, weighted by those scores. The result is a new vector for our token, now blended with the context that mattered most. That is a single attention head. That was one attention head, but a transformer runs many heads in parallel. 12, 16, sometimes far more. Each head gets its own query, key, and value projections, so each one can learn a different kind of relationship. One head might track which noun a pronoun refers to. Another follows the verb back to its subject. Another watches position, or tense. They all attend at the same time, over the same tokens. Then we line up their outputs side by side and pass them through one more linear layer, mixing them back into a single vector. Many different views of the sentence, combined into one. Two small steps wrap every sublayer, and they make deep transformers trainable. First, the residual connection. We take the sublayer's input and add it straight back to its output. Nothing gets replaced. The new information is just added on top. That gives gradients a clean path down, so even a very deep stack can train. Second, layer normalization. It rescales each vector to a steady mean and spread, so the numbers never blow up or vanish, layer after layer. In modern transformers, we normalize first, run the sublayer, then add, and norm. Small steps. But without them, depth falls apart. Attention let the tokens share information. The feed-forward network is where each token thinks for itself. It's a small two-layer network applied to every position separately, with the same weights. First, it expands the vector, usually to 4 times the width, opening up room to compute. A nonlinearity, like GLU, keeps the useful patterns and drops the rest. Then it projects back down to the original size. This is where much of the model's knowledge lives, the facts and patterns it recalls. Attention decides what to look at. The feed-forward layer decides what to make of it. One block does all of that. Attention then feed forward. Now we stack it. The output of one block becomes the input to the next, and we repeat. GPT-2 stacks 12. The biggest models stack 96 or more. Same shape at every layer, but each has its own learned weights, and the representation sharpens as it climbs. Early layers catch grammar and nearby words. Middle layers build phrases and meaning. The deepest layers hold abstract, high-level understanding. The same vector refined again and again until it is finally ready to predict. After the final block, we take the vector for the last position, the model's running guess at what comes next. One more LayerNorm. Then, a single linear layer maps that vector to a score for every token in the vocabulary. 50,000 numbers, one per possible token. These are the logits. Softmax turns them into probabilities. Now we just pick. Take the highest for the most likely word, or sample from the distribution to get something more creative. That dial is the temperature. Either way, one token comes out. So far, we predicted one token, but a sentence is many. Here's the trick. We take that new token, append it to the input, and run the whole stack again. The prediction becomes part of the prompt. Predict, append, repeat. The cat sat on. Now on is part of the input, and the model predicts the. Then, that. One full pass through the network for every single token. That is why text streams out word by word and why longer answers cost more. This loop is what autoregressive means. Let's put it all together. Your text becomes tokens. Each token becomes a vector, with its position baked in. Then, the stack. In every block, attention lets the token share context, and the feed-forward layer thinks on each one, wrapped in residuals and normalization. 12 blocks refining the meaning layer by layer. At the top, one projection turns the final vector into probabilities, and we pick the next token. Append it and run the whole thing again. That is the transformer. Tokens in, one token out, over and over, simple parts, stacked deep, and language falls out.